Bismillahirrahmanirrahim. Today we will start tensor, a linear transformation. We will define a linear transformation as a tensor, as a second order tensor, not first, not zeroth order, not first, not third, only second order tensor. That if you have a linear transformation, then that linear transformation is a second order tensor. And you know that we have two properties of a transformation to be linear. For a transformation to be linear, suppose that we have a transformation T and we have two vectors A and B, and this transformation transforms any vector into another vector. Suppose this transformation T transforms vector A into vector C and vector B into vector D. So we will write this thing as TA equals to C and TB equals to D, that T is acting on vector A and giving us C. Similarly, when T acts on vector B, we get vector D. So for the linear properties of this tensor T, of this transformation T, we will write these as T of A plus B equals to TA plus TB. This is the first linear property for linearity, and this is the second. This is the scalar multiple. T of alpha A is equal to alpha times TA. If any transformation T satisfies these two properties, then we will say that that transformation is a linear transformation. Here A and B are two arbitrary vectors and alpha is any arbitrary scalar. If the transformation is linear, then we will also say that this is a second order tensor, or simply a tensor. That throughout the whole course, whenever we say that we have a tensor, we mean that second order tensor. If we will talk about third order or first or zeroth order or fourth order, then we will say that we have third order tensor, fourth order tensor, or a vector or a scalar. But when we say a tensor, we mean that a second order tensor. Now you can combine these two properties in this equation. T of alpha A plus beta B equals to alpha TA plus beta TB. That these two can be written in one form as equation 2b 1.2, where alpha and b are arbitrary scalars. You can get these two from this equation. That if you will put alpha and beta 1, then you have this equation 2b 1.1a, and if you will put beta is equal to 0, then you will have this second equation. Now, when any two tensors can be equal, suppose that you have tensor T and tensor S, that you have two tensors T and S, and these tensors are transforming any vector A into a similar vector, that is that any vector A in an identical way, that T transforms A. Suppose that T of A is equal to B, that T is transforming A into vector B, and S is also transforming A into vector B. then we say that these two vectors are equal to each other, that is ta is equal to sa equal to, we can write ta is equal to s, that these both are equal to each other. If these vector transform any arbitrary vector in an identical way, then we will say that both tensors are equal to each other. Now in this example we have a transformation T, and we have defined this transformation, that how this transformation is transforming any vector. We have given that the transformation T is transforming every vector into a fixed vector n, that if you have a b c d e f any vector, then the result of that vector after transformation will be fixed vector, and this is the definition of the transformation. Now we will have to check there whether this transformation is a tensor or not. So for the transformation to be a tensor, we must check its linearity. If the transformation is linear, then we will say that this transformation is a tensor. Let us check. We will have to check its two properties. You know that we have already defined these two properties in these two equations. Suppose that we have any two vectors a and b. So by the definition of the tensor T, by the definition of the transformation T, we can write Ta is equal to n and Tb is equal to n. That, as we have said in its definition, that it will transform every vector into a fixed vector n. So AB are any two vectors, so T of A is equal to n, T of B is equal to n. So we can write T of A plus B is equal to n. How can we write this? Because A is a vector, B is a vector, their sum is also a vector, so A plus B is another vector. But this transformation T will transform that vector again to vector n. T of A plus B equals to n. So we can write that, we can see that Ta plus Tb is 2n, Ta plus Tb is 2n, n plus n, but left hand side this is n. So these are not equal. So it means that this T is not a linear transformation, so it is not a tensor. So the transformation in this example is not a tensor. No, here we have another example. Let T be a transformation. We transform every vector into a vector that is k times the original vector. Is this transformation a tensor? Now we have defined the transformation here in this example in such a way that the transformation T will transform any vector into a vector that vector should be the k times the vector which is being transformed. Now we have to check, is this type of transformation a tensor or not? To prove that this type of transformation is a tensor or not, we will have to check its linearity. Suppose that we have vectors a and b and its arbitrary scalars alpha and beta. By definition, T of A is equal to k times A. That transformation T is transforming this vector A into a vector which is multiple of this vector A, k times the original vector. A is the vector which is being transformed, and also Tb is equal to Kb. Now we will have to check its both properties. Either you can check with the help of this equation or these two equations. So if you want to check with the help of this equation, then you can write T of alpha A plus alpha B. This is left side of 2b 1.2. T of alpha A plus beta B equals to k times this k times. This is the definition of the transformation. A is a vector, B is a vector, alpha is also vector, beta B is also vector, their sum will also be a vector. So T will transform this vector into k times the original vector. Here the vector which is being transformed is alpha A plus beta B. So its result will be, after transformation, its result will be k times this vector, alpha A plus beta B. Now this is the left hand side. We will proceed with the help of this equation. We have written this thing as it is, and from here we can write alpha outside, and we have ka plus beta kb. These are simple the scalars, alpha and k. These two are scalars. K is also scalar, k is scalar, and alpha beta also k. So you can write this thing as, you can multiply k into alpha a plus beta into kb, and you know that ka is the ta and kb is the tb. So this is the required property. This is left hand side, and this is we have started from left hand side and we have get right hand side. Both are equal. So this transformation is linear transformation. So if it is linear transformation, then by definition it is a tensor, second order tensor. So in first example we have seen that transformation is not a tensor. In second example we have seen that transformation is a tensor. No, one thing more, that if k is 0, k is scalar, so it can be 0. If it is 0, then it means that this type of transformation will transform each vector into a 0 vector, So this type of transformation in which k is 0 is known as zero tensor. This tensor is known as zero tensor. This is the symbol for the zero tensor. Zero tensor. This is not zeroth order tensor. This is only zero tensor, not zeroth order tensor. Now I have left two examples, 1.3 and 1.4. Please do those two examples by yourself, by studying what is written there carefully. Now example this, we have tensor. We have given that we have tensor, and it is written that this tensor T is transforming A as T is equal to A plus 2B. We have two specific vectors A and B according to that TP tensor that transform the specific vectors A and B. This that we have taken any two specific tensor A and B, and these specific tensors A and B are being transformed with T in this way. T is equal to A plus 2B and TB is equal to A minus B. Now what we have to do, we have to find the transformed vector of this C, and C is in the form of 2A plus B. Basically we have to find TC, that when T acts on C, what we will get. So T of C equals to T, and we have used value of C here from here, 2A plus B. It would be equal this, as we have said that T is a tensor. T is a tensor, so we can write this thing as, by using the linear property. To Ta plus Tb, and Ta equals to this and Tb equals to this. So after simplification we have 3A plus 3b. That if tensor T transforms A and B in this way, then it will transform this C, this vector C, into this, that this will be equal to 3A plus 3b. No, components of a tensor. As you know that you have only one component to describe a scalar, and you need three components to describe a vector. So similarly, now we will go for the components of a tensor. That one component for scalar, three components for vector, and how many components for a tensor? Let's see. As we know that components of a vector depend on the base vectors used to describe the components. That you know that if you have any vector v equals to v1 e1 plus v2 e2 plus v3 e3, e1 e2 e3 are the base vectors. Now if you want to have component v1, then what will you do? You will simply take the dot product of this vector with e1, v dot left side, v dot e1 will be equal to v1 into e1 dot e1 plus v2 into e1 dot e2 plus v3 into e1 dot e3. The second and third term e1 dot e2 and e1 dot e3 will be equal to 0. So you and e1 dot e1 will be equal to 1. So you have v1, that is v dot e1, and similarly you can have v2, you can have v3. Now in the similar fashion we will use these base vectors e1 e2 e3 to get the components of vector, get the components of a tensor. Suppose that e1 e2 e3 are the unit vectors in the direction x1 x2 and x3 axis respectively. Along x1 we have e1, along x2 axis we have e2 x3 axis and e3 in a rectangular Cartesian coordinate system. Now as under a transformation T, these vectors are transformed. How? e1, e2, e3 are vectors, as we have said that if you have vector A and if the transformation T acts on A, you will have vector B. Now, here we have vectors e1, e2, e3 unit vectors, base vectors. So what we will do, we will see that T transform e1 into Te1, it will transform e2 into Te2, and it will transform e3 into Te3. This is the Tei, I is equal to 1, 2, 3. So being a vector Te1, Te2, Te3, we can write these in this way. Te1 equals to this, Te2 equals to this, Te3 equals to this. This is written in the as these are vectors. Similarly, as v vector is equal to v1 e1 plus v2 e2 plus v3 e3. So it means that coefficient of components of vector Te1. First component is T11, second component is T21. This is the notation that we are using in this, that we are writing second component of this vector Te1 as T21 and third is T31. Similarly for Te2 and similarly for Te3. No, we can write these three equations in this form, initial notation, that we can write Tei is equal to Tj I Ej. Now I is free index and j is dummy index. So if I is 1, then you have Te1 after expanding j, Te2 and Te3. Now you can get these equations, these components T11, T21, T31 by using the similar way as we have used, as you have used the vector as you have used to get the components of vector v. If you will take in similar way, that if you will take the dot product of e1 of with this equation, then what you will have, you will have e t e1 dot e1, and on right hand side you will have t11 e1 dot e1, t21 plus t21 e2 dot e1, t31 into e3 dot e1. These other two will be 0, and you will have simply t11 equals to e1 dot te1. Similarly, you can get second component, third component, then first component of this second. No, you for to get first component of this, you will again take the derivative. We take the dot product of this with e1. In this way, you will have these 9 components: t11, t12 up to t33. So you can write these 9 in this way, initial notations: tij equals to ei dot tej. Remember this form, that you will use again and again this form. That tensor components of tensor will be written in this way: tij equals to ei dot tej. You cannot write it as ej dot tei. You will get wrong answer if you will do this. Tij equals to ei dot tej. That is, you have 1 2, then you will get this 1 3, again you will have this component. Similarly, you will go on. Now, the components tij in the above equations, these equations are defined as the component of tensor T. As I have said that we get the components of vector v with the help of the base vectors by taking the derivative with e1, with e2 and e3, and we get v1, v2, v3. Similarly, we have taken the derivative of these 3 derivative dot product. I am saying derivative is not derivative, instead of derivative it is dot product. That we are taking the dot product of these 3 vectors with e1, e2 and e3, and you have got you are getting these 9 components. These 9 components are defined as the components of tensor T, and we will write in matrix form in this way: that first column are the components of first vector, second column are the components of second vector, and third column are the components of third vector. And this is the t11, t12, t. That is why we have written t11, t21, t31. Now this matrix is called the matrix of the tensor T with respect to the set of bases. That we have used these bases, and we have this type of matrix for tensor T with respect to basis ei for short. Now to get this is the example 2b1 2.1. In this example, we will ask you to get the components of tensor T, or the matrix of the tensor T. Matrix of tensor T means that you have to write the components of tensor T. So to get the components, or to get the matrix of tensor T, you must have the transformation of e1, e2 and e3. If you have the transformation of e1, e2 in e3, then it means that you can write the components of tensor. This is te1, this is te2, te3. You can simply write 4 1 0 2 0 3 minus 1 3 1 minus 1 3 1. This is the vector matrix. Now this is another example. In this example, we are saying that T is transforming every vector into its mirror image with respect to a fixed plane. Suppose that it is given that we have fixed plane x2, x3, and E1 is normal to that fixed plane. If E1 is normal to that fixed plane, then and x2 and x3 are is the fixed plane, So it means that E2 and E3 will not change because their image will be on that plane, because they are on the fixed plane, on the plane which is using as fixed plane. As it is written here, that since the normal to the reflection plane is transformed into its negative, normal will be transformed into its negative. So it will be TE1 equal to minus E1, and other vectors parallel to the plane are not altered. TE2 equal to E2 and TE3 equal to E3. This is the matrix for the vector T, and this is with respect to basis EI. Now if you have basis E1 dash, E2 dash and E3 dash in such a way that E1 dash and E2 dash on a plane perpendicular to the mirror, with each making 45 angle with the mirror, as that we have mirror, this is the mirror, and E1 E2 dash making the angle 45 with this E2, and E3 dash is simply pointing outward, here outward. So as we have seen that E1 dash is making angle 45 with E2, and E2 dash also making angle 45 with this E2, means that we have taken a mirror on this line which is parallel to E2. So it means that if we will transform TE1 dash about this mirror, then it means that we will get the image of TE1 dash equals to so simply E2 dash, E2 dash, and mirror image of this E2 dash will be E1 dash, and E3 dash will not change. So this is the matrix of tensor T with basis EI dash. That here we have mirror in this way, and E1 and E dash making angle 45 with this mirror. Now keep in mind that wherever we have written this matrix T, it means that, or this, it means that this is the matrix of tensor T with respect to basis EI, not dash. And wherever we have this dash is outside the bracket here, So this is the matrix of the same tensor T with respect to basis EI dash. Keep in mind, same tensor T, it will be written here, that, or this way, that we shall denote the matrix of tensor T, same tensor T with respect to basis EI in this way, and with respect to basis dash into this way. Now if you have the last two matrices should not be confused with this. Now if you have this, no, dash is inside the bracket, then it means that this is the matrix of tensor T dash with respect to basis EI. So it means that if dash is outside, then the matrix with respect to EI dash, and if dash is inside, then the matrix of T dash with respect to EI. So keep this thing in your mind. Thank you so much.